Hi there, warriors. This is Miss Lemons, and today we're going to be talking about the standard heats of formation. Before we get started, I do want to review a little bit of enthalpy. Remember, enthalpy describes the flow of heat in a system, and at certain conditions, Q, or heat, is equal to delta H, or enthalpy, the change in enthalpy. Enthalpy is represented by the symbol or variable capital H. It's measured using the unit kilojoules, or more commonly, kilojoules per mole. We cannot measure enthalpy directly. We can only measure the change in enthalpy, which is what we did in the calorimetry experiment, right? We measure Q, therefore we also get delta H, or the change in enthalpy. And then today we're going to be focusing on the symbol delta H naught. That little symbol there is not degrees. So delta H naught is used for energy changes at standard conditions, which is 25 degrees Celsius and 1 atm of pressure. And like I said, this will be the focus of today's video. So we were able to measure the delta H of a chemical reaction using calorimetry, but sometimes it can be really difficult to measure the delta H of a reaction. And there are 4 different scenarios where it's too difficult for us to measure delta H. We have to use other methods. So the first criteria, the first instance would be that some reactions happen too slowly, so slowly. How could you measure the change of energy of a reaction that happens over hundreds or thousands or even millions of years? We're not that patient, right? So that's a really difficult scenario for us to measure the delta H. The second difficult scenario for us to measure delta H is that some reactions happen too fast. So some reactions are too slow, some reactions are way too fast. They have these intermediate steps that last only for a split second. So this reaction right here, this happens probably for a split second. We don't even see any time to really gather any data on the delta H here. And then before we know it, we've created the products of this reaction. So it's too fast for us to measure. It can be really difficult to also measure the delta H of complex reactions. So for instance, an emerald is made out of chromium, aluminum, silicon, oxygen, and beryllium. It would be very, very difficult to break this gem down into its original materials and then also measure the change of enthalpy for the production or fit of each of those materials. And then finally, another instance, or the final instance of where it can be difficult for us to measure the delta H would be dependent on the conditions of the reaction. Sometimes we need to have specific conditions that are difficult for us to measure, and maybe it needs to be super, super hot or super, super cold or under intense pressure. And we just can't get the right tools into the apparatus to actually measure delta H. So we have to figure out a different way to measure the delta H of some of these reactions because it's just not possible by the methods that we currently have. So what do we do if we can't measure the delta H? How do we measure delta H in these tricky scenarios? We do have a few methods. So one of the methods, we need to make sure that all of the reactions take place at standard state conditions, or we have reactions take place at standard state conditions. And this is one of your vocab words. Standard state conditions just mean that the temperature is at 25 degrees Celsius and the pressure is at 1 atm. Okay? So why do we need them to actually measure these at standard state conditions? Like who cares? Well, the reason why is they measure the change in enthalpy, or the delta H of a reaction at standard states to work as a reference point for comparison, kind of our control variable, right? We can compare the change of enthalpy between 2 reactions if they happened at the same conditions, right? Under the same conditions, okay? Now, this is called the standard heat of the reaction, the delta H naught. Okay, so the delta H naught is the change in enthalpy of a reaction at standard state conditions. That is delta H naught, or the standard heat of reaction. And it's also measured in kilojoules per mole, just like delta H. So again, the standard heat of the reaction, the definition is the change in enthalpy of the reaction at standard state conditions. Okay, great. So you still haven't really told us how to measure delta H naught. Like, how do we get the standard heat of a reaction, the change of reaction at standard state conditions. Okay, well, to measure the standard heat of a reaction, we need to use what's called standard heats of formation. Okay, so the standard heats of formation is the change in enthalpy that's associated with the formation of 1 mole of compound from its elements at standard state conditions. Okay, so for instance, if you look at all 3 of these equations here, you can see that these are all examples of standard heats of formation. So we've got elements that are coming together to create a compound. So this delta HF naught, or standard heat of formation, is negative 393.5 kilojoules per mole. Okay, what that's referring to is that the standard heat of formation, or the change in enthalpy required to create CO2 from its atoms, which are carbon and oxygen, we need to release 393.5 kilojoules per mole of energy in order to create 1 mole of CO2 from its elements. Okay, so the standard heat of formation is the amount of energy required to create a substance from its elements. Okay, right? So we can actually create this substance here without using elements, right? We can do a double replacement reaction or a single replacement reaction, but we're really focusing on what does it take to create this substance just using its elements. So you can see that each of these standard heats of formation is different for each substance. So this would be the standard heat of formation for calcium oxide, and this would be the standard heat of formation for calcium carbonate. So the standard heat of the reaction, of a chemical reaction, can be calculated using the standard heats of formation and the equation below. The standard heat of reaction equals the sum of, and remember this from bond energies, the sum of the standard heats of formation of the products minus the sum of all of the standard heats of formation of the reactants. Okay? These standard heats of formation will always be given to you unless you have a singular element or a diatomic molecule. Those all have a standard heat of formation of 0 kilojoules per mole. This makes sense because it requires 0 energy to just exist as a singular atom, right? And we also know that diatomic molecules, remember there are 7 of them. They start at the number 7, so nitrogen, and they work their way down, plus hydrogen. Or you could think Han and the halogens for your diatomics. They naturally come together. They want to form that bond with each other. So O2 will never exist as just O. It will always be O bound to another O so that it exists as O2 or H2, Cl2, I2, Br2. These are all your diatomics, and they all have standard heats of formation of 0 kilojoules per mole, meaning they require no energy to create or break. Okay, and then I went ahead and I listed all of your halogens down below, your Han, H-O-N, Han, and the halogens, fluorine, chlorine, bromine, and iodine. So a quick recap, what we covered today. The standard heat of the reaction is the change in enthalpy of a chemical reaction in standard state conditions. In order to calculate the standard heat of a reaction, you need to use the standard heats of formation, which are given to you, unless, of course, we are using diatomics or singular elements. And it is measured in kilojoules per mole. Standard state is the perfect standard laboratory conditions. That means the temperature is at 25 degrees Celsius and it is 1 atm pressure. And then the standard heat of formation is the change in enthalpy that's associated with the formation of 1 mole of compound from its elements at standard state conditions. And it's measured in kilojoules per mole. And the elements and diatomic molecules have a standard heat of formation of 0 kilojoules per mole. Remember, we use standard heats of formation to help us calculate the standard heat of a reaction.